Okay, here's today's objective. We are going to be covering exponential functions today. Our goal is to be able to identify and graph exponential functions. As I do all these recordings, I would just like to say, with the power of YouTube, you have the ability to pause the video at any time, so I will not be waiting for many slides. So if you need more time on a slide, all you have to do is pause the video and then move it along when you are ready. Exponential functions. We know their general form is y equals a times b raised to the x power plus c. The y-intercept for an exponential function is always going to take the form of 0, a plus c. We're always going to have an asymptote at y equals c, which you don't know what an asymptote is probably right now, but I will cover that with you guys in a second here. And our range is always going to be y is greater than whatever our asymptote is. For the general form of an exponential function, I would like to let you guys know as well. The a value is your starting amount. The b value is your growth rate. So if I say something is doubling or it's tripling or quadrupling, that's your growth rate. And your c value is going to be your asymptote, which is the line that your graph gets really, really close to but never touches. Next up, we have exponential growth and decay for both of these things. So we can have things that grow exponentially, and we can have things that decay exponentially. As far as exponential growth goes, your b value is the growth factor. Your b must be greater than 1. And as your graph goes to the right, the exponential function is going to be rising, something like this. So as it goes to the right, notice it's going up faster and faster. In this case, we might have an asymptote right here. We don't know exactly what it is, but as you can see, it's a line that our graph gets closer and closer and closer to, but it never touches. On the other hand, we have decay. For decay, b is your decay factor. b must be between 0 and 1. Many students make the mistake, they think b has to be a negative number, and that's actually not true. b has to be between 0 and 1. As it goes to the right, your graph is going to be falling this time. So what that might look like is something like this. We start up high, and it goes nice and low like that, and still gets closer and closer and closer to our asymptote, but it never ever touches it. Next up, we're going to practice identifying whether something is growth or decay. So what we are going to actually be looking at is our b values. So that's our b value on our first one. This would be our b value on our second one. This is our b value on our third one. This is our b value on our fourth one. Now what we are trying to look for here is we are deciding if that number is bigger than 1. If it's bigger than 1, it's going to be growth. If it is between 0 and 1, it's going to be decay. So 0.25 is going to be between 0 and 1, so that is going to be decay. 1/4 is between 0 and 1, so that is going to be decay. 6 is greater than 1, so that's going to be growth. 5/2 is greater than 1, so that's going to be growth. Next up, we are going to be doing some graphing here, which I will tell you that I am cheating slightly. I am going to be using a graphing calculator off screen here to be able to get these numbers. If you have a graphing calculator, great. Feel free to type it in on y equals, and you can look at the table and get these numbers. If you do not have a graphing calculator, that is A-OK. You can simply just copy the numbers that I come up with. But once again, if you want to get the numbers that I am looking for here, just so you know, I always am going to be looking at the table on my graphing calculator. When we are doing exponential growth, I always start at -1 for my x value, and then I just go 0, 1, 2, 3. Now, once again, what I am going to be doing is typing this equation into my calculator right now, so I will do that really quickly. And I am going to pull up the table on my calculator. Once I do that, I can see that my values are 0.33, 1, 3, 9, and 27. Now, something that I would like to kind of let you guys know as well is that our growth factor was 3, as you can see. So our growth factor is 3. So it makes sense that our numbers are tripling every single time. And that's kind of how that would be working. So every single time we are saying times 3, times 3, times 3, times 3. That's what makes it exponential growth. It is multiplying by the same number every single time. The next thing that I'm going to be doing is I'm going to be looking at the y-intercept. So if you remember, that's always when your x value is 0. So there's two ways to do that. If you have a graphing calculator, you can look on the table when your y value is 0. If you do not, you can plug in 0 for the x value and see what you would get for the y value. In this case, your y-intercept is going to be 0, 1. Your domain for these, there is no limit on our x values. These are all of our possible x values, remember. So our domain is going to be all real numbers. There is no limit on the x values that we can use in this situation. Next up, we have our asymptote. The asymptote is always going to be the c value. That's going to be the number that's added or subtracted on the end. So it always takes the form of x equals whatever that c value is on the end of your equation. In this case, we have nothing, so I could rewrite this as y equals 3 to the x power plus 0. We have nothing added there. So our asymptote is going to be at x equals 0. The final thing that we have is the range. The range is always going to take the form of y is greater than whatever your asymptote is. And in this case, we already know our asymptote is 0, so our range is going to be y is greater than 0. Now, I'm going to do a quick graph here. All I'm going to do to graph this thing is simply plot the numbers that are on my table. So I have, actually, I'm sorry, before I do that, I'm actually going to draw my asymptote in. So here I have x equals 0 is my asymptote. And now I'm going to actually plot those numbers on the table. So I have negative 1.33, 0, 1, 1, 3, 2, 9, and 327, which is way off my graph, so I actually don't have to graph that one. And then I simply just draw my line. A huge key on this is make sure your graph does not ever touch your asymptote. It gets really close to it, but it does not touch it. Next up, we are going to have another equation here, so I will type this equation in on my calculator really quick. I'll give you a second to do that as well. And when I look at my table, I'm actually going to start at -1 again here. So I have -1, 0, 1, 2, 3. And it really doesn't matter where you start your table at. You could start it at -2 if you wanted to. I just like to start it at -1. There's no real rule between that. So my y values are 5, 3, 2, 1.5, and 1.25. The y-intercept here, looking at the table on my calculator, is going to be 0, 3. The domain is going to be all real numbers. The asymptote is going to be, this time I have a +1 right there, so it's going to be x equals 1, and my range is going to be y is greater than 1. So when I go over and graph this thing, I'm going to graph it at y equals 1 here first. I got to do my asymptote. After I do my asymptote, I'm going to plot my points, and then I will be able to draw my graph. So I have -1, 5, 0, 3, 1, 2, 2, 1.5, and 3, 1.25. Go ahead and graph that guy. And we are all set to go there. Our next slide here is to decide if a function is an exponential function, and we actually already talked about that earlier. We said you have to look at the growth factor here. So basically what we need to do is figure out our pattern for our y values right here. That's what our goal is. Now, I am noticing that this pattern, to go from 8 to 4, I could divide by 2. To go from 4 to 2, I could divide by 2. To go from 2 to 1, I could divide by 2. Because I have a common factor, which is that I'm dividing by 2 every single time, that means that this is an exponential function. So we would say this is exponential. Next up, I'm still only looking at the y values. So to go from 4 to 7, if I use my calculator, I can do 4 divided by 7 and figure out that that is 0.57. So if I divide that by 0.57, I would get that. To go from 7 to 10, so I can do 7 divided by 10, that is 0.7. And to go from 10 to 13, that is 0.77, which that is not a common factor. If I actually wanted to do this one, I could notice that the pattern is actually +3 every single time. +3, which actually means this thing is going to be linear. So if it is linear, it is not exponential. Not exponential. And let's keep on going. So the final problem that we have for today is to suppose a pond of fish doubles every single week. So my growth rate is going to be times 2 because it's doubling. The pond starts with 4 fish. So my starting value is going to be 4 fish. So that's my starting value. Now, this thing tells me to write an exponential function for the fish for x weeks. That means we don't know how many weeks it's going to be, so we're going to have a total number of fish. We say our starting value first, which our starting value is 4, times, we need to know our growth rate, which we know our growth rate is 2. So we can say 2 raised to the x power. There is no asymptote that was given to us, so that is actually our equation right there. From here, this problem is basically just a calculator problem. All you would have to do is you can type this equation in on your calculator, which you're going to go ahead, you're going to say y equals 4 times 2 raised to the x power. And it says how many fish will there be after 6 weeks. So there's 2 ways to do this. You can look on your calculator table, which is actually what I'm doing right now. If you do not have a calculator table, what you can do is you can say, okay, y equals 4 times 2 raised to the 6th power. If you do that, you would figure out that there would be 256 fish. Now, how many weeks will it take to get to 64 fish? So what you can do on this one, notice we are not given the number of weeks this time, we're actually given the number of fish. So we need to plug in 64 equals 4 times 2 raised to the x power. I can divide both sides by 4 on this. If I do that, I actually get 16 equals 2 raised to the x power. And when I do that, I know that my answer is 4 weeks. The other way that you could do that is use your graphing calculator, and you could simply scroll down until you saw when you would have 64 fish. How many days will it take to get to 64 fish? So this is kind of a little bit of a trick problem, but we've been dealing in weeks so far, but this time we're actually going to be dealing in days. So if it took 4 weeks to get 64 fish, how many days would that be? Well, there's 7 days in a week, and 4 weeks have passed, so it's going to be 28 days. That's kind of a thinker for you. That is it for our lesson today. I would hope that you have a great rest of your day and enjoy yourself.